Since the streamlines are curved, there must be a normal pressure gradient, with the pressure at the cylinder surface less than the atmospheric pressure at the outside boundary of the jet. The manometer shows that the pressure is less than atmospheric. Because now the manometer is balanced again. The Coanda effect is also part of the explanation for this. So far, we've looked separately at the pressure gradients along and normal to the streamline. To understand a complete flow pattern, however, we must consider both of these. And of course, we must also consider the equation of continuity to ensure that mass is conserved. Our flexible wall rig now is in the form of half of a rapid symmetrical contraction. Upstream, the pressures are equal on both walls. Downstream, they are also equal, but lower. Because of the area decrease, the average velocity increases, and, according to the streamwise equation of motion, the average pressure falls. On the straight wall, the pressure falls continuously, but on the curved wall, it first rises, then undershoots to a very low pressure before reaching its final value. Here are the pressure distributions superposed. Let's see how these pressure distributions may be predicted by the two dynamical equations and the equation of continuity. This curve of pressure versus distance shows the average streamwise pressure variation associated with the one-dimensional average velocity at each cross-section. Far upstream and far downstream, where the streamlines have no curvature, the pressure will be uniform over the two cross-sections. From the shape of the channel, we may expect that the streamlines will be of this general shape: concave up in this region, concave down in this region. These are two curves normal to the streamlines in the regions of different concavity. And these are the directions of increasing n, that is, outward from the center of streamline curvature. From a one-dimensional point of view and a comparison of cross-sectional areas, we may expect the average pressure on AB to be only slightly less than the upstream pressure. But because of streamline curvature, the pressure increases from A to B, so that the pressure at B will be greater than the pressure at A. Similarly, the average pressure on CD will be only slightly greater than the downstream pressure. Again, though, because of streamline curvature, the pressure will increase from C to D. So the pressure at D will be greater than the average, while the pressure at C will be less than the average. So the pressure on the curved wall rises to a maximum at B and then falls to a minimum at C. While on the straight wall, it falls continuously from A to D. According to Bernoulli's integral, which in this case has the same value for all streamlines, the velocity is a minimum where the pressure is highest, and it is a maximum where the pressure is least. The hydrogen bubbles verify this velocity distribution. The tilting of these fluid lines shows that the velocity on the curved wall is at first less than on the straight wall. Here, near the beginning of the curve, the increase of stream tube area between the streamline and the curved wall shows that the velocity on the curved wall at first decreases. Near the end of the curve, the stream tube area reaches a minimum before once again increasing slightly. This minimum corresponds to the point of minimum pressure. Where the pressure rises on the curved wall, the viscous boundary layer thickens. If a rising pressure gradient is severe enough, the boundary layer might separate, or a laminar layer might become turbulent. To minimize adverse pressure gradients in wind tunnel nozzles, the contraction is made more gentle, as here. The streamline curvature is now much less, and the normal pressure gradients which caused the distinctive peaks in the pressure distribution are reduced. The flow is more nearly one-dimensional, and the pressure distributions on the two walls are more nearly alike. Bernoulli's integral is based on many restrictive assumptions. The statement that high velocity means low pressure is only sometimes true. Let's see how one could go astray. This straight duct has a partition. One side is free and clear. The other side has a flow resistance. Downstream of the partition, the two streams rejoin. The static pressures shown by these two manometers are equal. If you used Bernoulli's integral, you might conclude that the velocities of the two streams are also equal. Let's see. These are stagnation pressures, read by pitot tubes. From the two dynamic pressures, we see that the velocity downstream of the obstructed passage is less than for the clear passage. The reason Bernoulli's integral cannot be used here is that we are dealing with different streamlines. Because of the confinement of the channel walls, the streamlines are straight, with no curvature, and no normal pressure gradient. So the pressures on the two sides are the same, even though the velocities differ. For the same reason, the pressure across a viscous boundary layer is virtually constant. These vertical tubes will show the pressure distribution in the tank of water when we rotate it on the turntable. After viscosity brings the water into a solid body rotation, the velocity will increase linearly with radius. If you used Bernoulli's integral, which would be improper because you would be crossing streamlines, you would expect the pressure to decrease with radius. Actually, you see, the pressure increases with radius. This means that the stagnation pressure also increases with radius, and each circular streamline must have a different Bernoulli constant. The right way to look at this is with our familiar equation relating to streamline curvature. The outward radial pressure rise produces the net force which accompanies the centripetal acceleration. We have seen in this film a number of flows where the acceleration of each fluid particle was mainly produced by a single kind of force, the gradient of the pressure field. Finally, we must remember that we have left out many forces: gravity, electromagnetic, and so on. If these were present, the pressure field would have to balance them, as well as the inertial forces.